In today's video, I talk about statistical modeling. What do I mean by this? Well, one could say briefly, statistical modeling is the description of random effects by finding an appropriate underlying distribution. I assume you have some familiarity with statistical distributions, and I will give a few examples, a few important examples in the rest of this video. It is based on the script example underscore statmod, and we start as usual with a preamble. So let me skip to line 3. I set some colors, and we take advantage of the predefined distributions in the Matlab statistical toolbox. There's quite a few of them. Let's make a list of all predefined distributions. We'll use only a small part of this list. And you see them in the command window. So there are beta, binomial, Burr, gamma, quite a lot of them. Of course, all the important distributions like normal, gamma, Poisson, exponential are in this list. Let's start with the most important of them all. This is the normal or Gaussian or Gauss-Laplace distribution. I assume that you already know something about the normal distribution. If not, we can look up its most important properties in Wikipedia. So let's have a quick look at the wiki page of the normal distribution. Here we are. You see the shape of the probability density function, the well-known bell curve. It depends on two parameters, mu, the mean value, and sigma, the standard deviation, or sigma squared, the variance. Please have a look at this page if you're not that familiar with the normal distribution. So I return to my Matlab window. We can define a distribution object by calling the function makeDist, and the argument is one of the names in the list we have seen in the command window. So the name is normal, and we can now generate such an object. It's of class prob and then subclass normal distribution. We can have a look at the field names of such an object, and you'll see the parameters, which are mu and sigma for the normal distribution, the name, the number of parameters. We can truncate the distribution, we'll see that later, and so on. There's also a couple of methods which allows us to, for instance, plot the probability density function, the cumulative distribution function, the quantile function, the median, the mean, the standard deviation, the variance. And it allows us, with the method random, to generate random numbers from this distribution. Let's have a quick look at the most important characteristics. These are the mean, the variance, the standard deviation, the median, and the interquartile range. We will see in a minute what this means geometrically. So let me plot the distribution. I call a private function plot dist. You can have a look into this function later. Right, so this is a standard normal distribution with mean 0 and standard deviation and variance of 1. In figure 1, in the top panel, you see the probability density function. You see the mean and the median, they are both at 0. Since the distribution is symmetric, the mean and the median are identical. I also have plotted the mean minus 1 standard deviation. This is the line at -1, and the mean plus 1 standard deviation, that's the vertical line at +1. The inflection point of the normal PDF is just at mean plus 1 standard deviation and mean minus 1 standard deviation. In the two bottom panels, you see the normal CDF, the cumulative distribution function, which is just the integral from -infinity to x over the PDF. And you also see on the right hand bottom panel the normal inverse CDF or quantile function, which is the inverse function of the CDF. And in this function, you can see the median at the value Q0.5. It's at 0. You also see the quartiles, so the quantiles to levels 0.25 and 0.27. So this allows you to visualize the quantiles of the standard normal distribution. Now, the normal distribution is actually a parametric class of distributions parameterized by mean and variance or standard deviation. Please note that in Matlab, the second parameter is not a variance but a standard deviation. So let's define a different normal distribution with mean 2. Line 21, I set the mean to 2. Line 22, I set the sigma, the standard deviation, to 1.5. You have to know how the parameters are called, and you can see this in the field names of this object. So the parameters are called mu and sigma. So let's make a similar plot for this more general normal distribution. Okay, the shape is the same as before, it's just translated and scaled. And you see again in the top panel the PDF with mean, median, and mean plus minus 1 standard deviation. And in the bottom panels you see again the CDF, the cumulative distribution function, and the quantile function on the right-hand side. Now we want to generate a random sample from this distribution and then try to fit a normal distribution to this data. And then we'll see how well we can reproduce the true parameters. So I generate a random sample from this distribution object by calling the method random, and the arguments are just dimensions of a vector or a matrix. So in this case, I generate a column vector of length 500 in line 29. Now we fit a distribution to these data. The data are in the random vector R. So let's step into this function fit_dist, a private function of mine, and let's see how this is done. So let's step into fit_dist. I create a figure. I extract the name. This is just for bookkeeping purposes, so we can plot a nice title. I check whether it's a truncated distribution. Well, it's not truncated. I set the subplot. I histogram the data with the function histogram. So this generates the experimental histogram on the right-hand side in figure 3 in the top panel. So this these are the counts of the observations in the various groups. This is a histogram, a grouped count of observations. So let's now plot the true PDF. By true, I mean the PDF of the distribution from which this sample was generated. And now we call the function fitDist, which fits a distribution, a normal distribution in this case, to the data. So it estimates the parameters of a normal distribution which best fits to this data. So R, line 199, is the data, and the fit type in this case is normal. So it fits a normal distribution, and we can immediately plot the fitted PDF, which in this case is almost identical to the true PDF. So we have a legend, the blue bars are the histogram, the red line is a true PDF, and the yellow line or light brown line is the PDF of the fitted normal distribution. The two almost coincide. So let's return to our main script. And this terminates my example with a normal distribution. Next, I want to show an example with a distribution which is maybe less familiar. It's a gamma distribution. The normal distribution is frequently used for modeling symmetric random effects, for instance, measurement errors or similar random effects. The gamma distribution is used for modeling of positive and possibly asymmetric random effects. Let's have a quick look in the Wikipedia page. So here we see the gamma distribution. It has two parameters, a shape parameter and a scale parameter. The shape parameter controls, as its name says, the shape of the PDF, and the scale parameter is just a scaling factor on the x-axis. If you don't know the gamma distribution, please have a look in more detail in this page in the Wikipedia. So I return to the Matlab window. And now I make a gamma distribution by calling makeDist and then the name gamma. Now the default values of shape and scale parameters, they are called A and B in this case. They are both 1. I want to show an example with different values, so I set A to 6 and B to 2. Now let's have a look at the characteristic quantities. The mean value is A times B, so it's 12. The variance is A times B squared, so it's 24. The standard deviation is the root of 24, close to 5. The median is now different from the mean value. It's about 11.34, and the interquartile range is 6.4. Now let's make a graphical representation. I need to find out the significant range of this distribution, so I get the 99.9% quantile and the 0.1% quantile. So most of the mass of the distribution is contained in this range. And now we can plot the gamma distribution, this particular gamma distribution. And we see again the PDF in the top panel. Now the mean is the red dashed line. The median is somewhat smaller. This is typically for asymmetric distribution. The mean is most of the times larger than the median. And then we see the mean minus 1 standard deviation and the mean plus 1 standard deviation. I recall that in the normal distribution, these points were at the inflection points of the PDF. In this case, with the gamma PDF, there is no obvious geometrical interpretation of these points, mean plus minus 1 standard deviation. In the bottom panels, we see again the CDF, the integral of the PDF, and the inverse CDF, the quantile function. If you want to know the median of this distribution, you look at the point Q equals 0.5 at the quantile distribution, and then the Y value will tell you the median. It's about, where is the median? It's about 11.34. Now let's play the same game as before. We generate a random sample from this distribution. By using the method random. And now we fit a gamma distribution to this random data. You already seen how that works, so let's just step to the next line. We see again the histogram of the random sample, so the grouped frequency counts. And then we see the true PDF of the gamma distribution from which these data were generated in red, and we see in yellow the fitted PDF, which is again very close to the true PDF. Now we can try something else. We can try to fit a normal distribution to this data. Of course, we expect this to be not such a good fit. So let's see what a fitted normal distribution looks like if estimated from these data, which are actually gamma distributed. So we invoke again my private function fit_dist. It's at the bottom of the script. And let's see what the resulting normal distribution looks like. We see this in the bottom panel. So the data are from a gamma distribution, but the fit is now a normal distribution. And of course, we see that the fit is much worse than the fit with a gamma distribution. This is to be expected. There's a way of quantifying the goodness of the fit, and in this case it's the value of the log likelihood function of the fit. There is a method which gives us the negative log likelihood function of the distribution. It's called neg_log_lik in line 53. I take the negative to get the value of the actual log likelihood function. This value don't mean very much on their own, but they can be used to compare the fit. And we would expect that the log likelihood of the fitted gamma is larger than the log likelihood of the fitted normal. And we can use the function assert to check this. And we don't get an error, so the assertion is true. So this is a very convenient way of comparing the goodness of fit for two statistical models. I now stop this video at this point and continue in the next video.